video we'll use series sum, LINEST, in the polynomial regression of the natural logarithm ln 1 plus x. Here we have an expansion of the logarithm, the Maclaurin expansion of this logarithm ln 1 plus x, which is equal to the summation of negative 1 to the power n plus 1 times x to the n over n. In the series form, the expansion of this is 1, that is x minus x squared over 2 plus x cubed over 3 minus x to the power 4 over 4 plus x to the fifth over 5. So we have an alternating values of 1 and negative 1. So we begin with the data set for ln 1 plus x. So our data set will range from negative 0.8 to positive 0.8 of the x values. So we have our formula ln 1 plus x values. And we show the chart, how it looks like. So insert the chart. We use this color chart. And we'll also show the trend line equation that fits best to this chart. We cannot use linear because some points in the datasets are not in the line. We cannot use power series because only the positive portion are in the line. We cannot use logarithmic because it doesn't fit well. We cannot use exponential because the negative part cannot be in the line. So we'll use the polynomial. So that's the power 2, the degree 2. And the fitness, the goodness of fit is 0.988. We can make that better. So we go to the third degree. Now it's better, 0.998. It's very close to 1. So our polynomial regression is third degree raised to the power 3. And we will work on the expansion of the ln 1 plus x. Here's the expansion of ln 1 plus x. We'll start with the n values, which starts from 1 to infinity. This time we'll only work within the limits of our dataset range. So it is 1 until 9. Now we'll calculate this negative 1 to the power n plus 1 over n, the coefficient. So we start with the alternating values of negative 1. So it is array formula of negative 1 to the power n plus 1. And that is n, the n values, plus 1. We have an alternating. So we have positive 1, negative 1, positive 1, negative 1. That's positive 1, negative 1, positive. And we divide this by n. So we divide this third by n, divided by the n values. Now we have the coefficients. Now we can enter the series sum. You can use series sum to generate the data set of the expansion, which is array formula, series sum of the x values raised to the power, the starting power is 1, so it's 1, incremented by, so x raised to the power 1, to the power 2, to the power 3, so incremented by 1, and the coefficients, these coefficients. So we have the range of the coefficients. So our values, the expansion is a good approximation of our function. So the value here is almost the same. So we insert this into the chart. Edit, add a series, and this range. Now we have the chart. We'll also include the trend line, the same trend line, that is polynomial to the power 3. And you show the equation and as well as the goodness of fit. So the goodness of it is 0.999. It's better than the original, which is 0.998, because we're regressing this in the polynomial to the third degree. And we have the values of B0, B1, and B3, B2 and B3, B0, B1, B2, and B3. We'll calculate these values using LINEST. To do that, we have to, because here's the LINEST, we have to enter the x column, x squared column, and the x cubed column. We start with the x column, which is array formula of the x values raised to the power 1. And the x column will be array formula of the x values raised to the power 2. And the x cubed column will be array formula of the x values raised to the power 3. Now we can enter the LINEST function. We can use the LINEST function of data y. We start with the blue one, the original, and data x. Our B0, 0.02685, rounded off 0.0269. B1 is 0.936488, rounded off as 0.936. And our B2, so that's our B1, this is our B2, negative 0.80198, rounded off as negative 0.802. And our B3 is 0.672666, rounded off as 0.673. We now go to the expansion, which is LINEST of data y and data x. Our B0 is 0.0266. It's the same. It's also 0.0266 or 226. Our B1 is 0.9486. It is rounded as 0.949. Our B2 is negative 0.76565, rounded as negative 0.766. And our B3 is 0.621, rounded as 0.622. This completes the use of series sum and LINEST in the polynomial regression of the natural logarithm 1 plus x in the expanded in the Maclaurin series expansion.